guys, today we're going to be taking a look at intermolecular forces. So the first thing that we're going to be discussing is what exactly intermolecular forces are. So as the name suggests, these forces exist between molecules that are covalently bonded. So for example, if you have two water molecules over here, H2O and H2O, so the rectangles over here represent the molecules. The forces of attraction between these two are going to be termed as intermolecular forces. So one thing that's very important to note that these forces are different from actual covalent bonds. So the covalent bonds are going to be present between the atoms. However, the intermolecular forces are present between the molecules. So it's very important to understand this distinction. And these forces are going to be much weaker than actual covalent bonds. And the physical properties of the compounds are going to depend on the type of intermolecular forces. So by physical properties, I mean the boiling point, melting point, density, etc. And we're going to discuss this in detail later on. So the main types of intermolecular forces that are there are going to be instantaneous dipole-induced dipole, which is also known as Idid forces, permanent dipole, which is known as PD forces, and hydrogen bonding. And as you go down this list, the strength of these forces is going to increase. So Idid forces are going to be the weakest and hydrogen bonds are going to be the strongest. So the first type of intermolecular force that we're going to be discussing is instantaneous dipole-induced dipole or Idid forces. And this type of force is also known as van der Waals forces of attraction. So we're going to be talking about two situations. The first thing that I want you to look at is these two molecules that are there in blue. So you have two molecules of CH4, which is methane. Now one important thing that you need to note down is that these type of forces are going to be present in all molecules. It doesn't matter whether the molecule is polar or non-polar. These forces are going to be present in all of the molecules, but they're going to be the most dominant force in the non-polar molecules. So the electrons that are within a molecule, these are going to be constantly moving. So if you look at this diagram over here, the blue one, the one with the sides marked A and B. So at one instant, there are going to be more electrons towards A, and at some other instant, there could be more electrons towards side B. So the side which has more electrons compared to the other is going to be constantly changing because these electrons are constantly moving. This is going to lead to the formation of a fluctuating dipole. So if you look at this particular instant, the one that I've made in blue, there are more electrons towards side B, which is why it's going to have a partial negative dipole, and there are less electrons towards side A, which is why it's going to have a partial positive dipole. And this is only there at one instant. And this dipole is going to induce a corresponding dipole in the neighboring molecule. So in this case, the neighboring molecule is made over here. So if you have a partial negative charge towards B, it's going to induce a partial positive on this side and a partial negative on this side. So you'll have more electrons over here than over here. And this is going to lead to attraction because the opposite dipoles, partial negative and partial positive, are going to attract each other. Now one important thing to note over here that these forces are very, very weak. Like I mentioned before, these are the weakest form of intermolecular forces that you can have. Now the word fluctuating tells you that this dipole is going to be instantaneous, which means that at one instant A is going to have more electrons. For example, over here A has more electrons compared to B. So A will have a partial negative charge and B will have a partial positive charge, which is the complete opposite of what you can see in the blue molecules. So these blue and green molecules represent two completely different instances. So at one instance, A will have more electrons, and at the other instance, B will have more electrons. And this is going to change the neighboring dipole. So this is going to be partial negative, so it's going to have more electrons. And over here, it's going to be partial positive, so it's going to have less electrons. So the side which has more electrons is going to keep on changing in this case, which is why it's called instantaneous dipole, because it's going to keep on changing. And it's called induced because it's going to induce a dipole in the neighboring molecule. The next thing that we're going to be taking a look at is the factors that affect the strength of Idid forces. So the first factor that we're going to be talking about is the number of electrons that are present. So the larger the MR or the AR, the more polarizable electrons you're going to have. And this is going to lead to stronger Idid forces. So let's take a look at group 0. As you go down the group, the number of electrons is going to increase because the AR increases. And because of that, the boiling point of the molecules also increases. As you can see from this chain, the boiling point of helium is minus 269 degrees Celsius. For neon, it's minus 249. For argon, it's minus 186, and so on. So the boiling point is increasing. And the reason for that is that the number of polarizable electrons is going to increase. And because of that, the Idid forces are going to become stronger and more energy will be required to break them. So previously I discussed that intermolecular forces are going to affect the physical properties. So this is an example of that, which is the boiling point that is getting affected by the intermolecular forces. So if your intermolecular forces are stronger, the boiling point will be more because more energy is going to be needed to break them. So for example, if one molecule A has hydrogen bonds as its predominant force and molecule B has Idid forces as its predominant force. Like I discussed previously, hydrogen bonds are going to be stronger. So it's going to take more energy to break these, which is why the boiling point of substance A is going to be higher. And for this one, the boiling point will be lower. So this is an example of one factor that affects Idid forces and also an example of how intermolecular forces affect one physical property, which is the boiling point. The next factor that we're going to be discussing is molecular shape. Now this refers to whether a molecule is highly branched or it's a straight chain. For example, if we look at butane, which is C4H10, it can either be unbranched, which is mainly a straight chain molecule like this, or it can be branched. As you can see, this methyl group over here, CH3, is branched. So this is a branched molecule of butane and this is an unbranched molecule of butane. Now if you look at the boiling point, for this it's 36 degrees Celsius and for the branched molecule it's 9 degrees Celsius. So branched molecules have a lesser boiling point than unbranched ones. This means that for this, the Idid forces are going to be weaker. So less energy is going to be required to break them, and because of that, the boiling point will be lower. Now the reason for this is that in a straight chain or unbranched molecule, the molecule can easily pack close to each other. So because of that, there's going to be more points of contact. If you look at these two molecules over here, which are straight chain molecules, there's going to be more points of contact, which is why the forces are going to be stronger, as opposed to a branch molecule in which the molecules are going to be somewhat spherical, so it's going to be difficult for them to pack close to each other, and because of that there's going to be fewer points of contact. As you can see, it's difficult for these two molecules to pack close together compared to these two molecules. So the forces of attraction are going to be stronger in an unbranched molecule than in a branched molecule. So this is the second factor that affects the strength of the Idid forces. So the next intermolecular force of attraction that we're going to be discussing is permanent dipole force of attraction, or PD force of attraction. So one important thing to note over here that this is present in polar molecules. So if you have a non-polar molecule like methane, which we discussed previously, PD forces are not going to be present because it's non-polar. And if you're confused about electronegativity and polarity, there's a video on that, so you can go check that out. So the example that we're going to be looking at for this video is going to be HCl. So in this case, chlorine is more electronegative than hydrogen, so it's going to have a partial negative charge, and hydrogen will have a partial positive charge. Unlike the molecules in Idid forces, these dipoles are permanent, which means that hydrogen will always have a partial positive charge and chlorine will always have a partial negative charge. Now these dipoles are going to attract each other, which means that this partial negative and this partial positive will attract each other, and this is going to result in the intermolecular force, which is PD forces. and these dipoles would not cancel out. Another example that we can look at is methanol. So in this case, oxygen is more electronegative, so it's going to have a partial negative charge, and hydrogen is going to have a partial positive charge. So this partial negative will be attracted to these partial positives, and it's going to result in the intermolecular force of attraction.